Welcome to the Deep Dive. If you're starting your journey as an aviation maintenance technician, Chapter 1 of the General Handbook, Safety, Ground Operations, and Servicing,
hmm
well, it's a bedrock.
It really is.
We're not just reciting facts today. We're aiming to accelerate your understanding of the really high-stakes details. The kind of knowledge that separates someone who just passed the test from a safe, effective technician out there on the flight line.
That's precisely the mission. Yeah, this chapter is absolutely critical because, look, as an AMT, you must be proficient with complex ground support equipment.
Right.
But maybe more importantly, you have to understand the hidden hazards, things involved in ground handling, servicing, taxiing, even engine run-ups. We're focusing on those details that bridge the theory and the actual practice, the must-know protocols that govern how we interact with these massive, powerful machines.
And interestingly, before we even touch a wrench or think about a tow bar, we have to look inward. We're starting not with the equipment itself, but with the element that, well, it causes the most maintenance errors in the industry, hands down.
The human element.
Exactly, the human element. Okay, let's unpack this a bit.
Yeah, what's fascinating here is the required introduction of human factors into maintenance performance. It's become central.
Right.
Safety isn't just about following checklists, it's really about self-awareness. You need to understand how internal things and external pressures too, they directly compromise your ability to perform maintenance safely.
So what kind of factors are we talking about?
Well, the key areas that frequently lead to errors include things like fatigue, obviously, deadline pressure, stress, distractions, poor communication skills, complacency, that feeling, that it won't happen to me.
Yeah, that's a dangerous one.
It is, and sometimes just a simple lack of information. This isn't like touchy-feely stuff. This cognitive awareness is genuinely essential for your personal survival and, honestly, the collective safety of the entire ramp.
And that self-awareness has to extend immediately to the physical environment around you.
Absolutely.
We're talking about shop safety, an orderly, clean work arrangement in the shops, in the hangars, and out on the flight line. It's just non-negotiable, because if you are stressed or feeling complacent, a messy environment is just, well, it's a ticking clock for a mistake, isn't it?
Exactly. And that standard of cleanliness, it's often really tested during a shift change.
Ah, good point.
If you're on the outgoing shift, it's your duty to remove and properly store all your personal tools, stands, hoses, electrical cords, everything.
Right.
That kind of procedural discipline ensures the next team doesn't walk into a foreign object damage or FOD hazard before they even start their day.
So if internal communication starts with that self-awareness, then external communication, maybe it starts with the floor itself.
How do you mean?
Well, those visual communication aids, you need to look out for the painted safety lanes, the pedestrian walkways, the fire lanes inside hangars.
Ah, okay.
Yeah. They keep people safe by clearly designating movement zones.
Mm-hmm.
And importantly, if you see others acting unsafely, you actually have a duty to speak up.
That's crucial. Ignoring a hazard is basically accepting it.
Exactly.
Okay, so let's transition then. From cognitive safety, let's talk about managing raw energy, starting with electrical safety.
Okay.
Physiologically, an electrical current can cause, well, severe burns, both entrance and exit points, and potentially permanent damage to the nervous system.
Nasty stuff.
But what's often overlooked are the psychological factors. The two major causes of electrical accidents are actually fear, often just due to a lack of knowledge. And the flip side, overconfidence. That's what leads technicians to take unnecessary risks.
Right. So the proper PPE, like the rubber gloves, the grounded safety mats, they're not just a physical barrier.
No, they also help manage that psychological tension. They build confidence based on real protection, not just bravado.
And heat. Heat is the silent killer when current's involved, right? We need to talk about electrical fire prevention.
Absolutely. Heat is a constant byproduct of current flow. It's just physics.
So how do we prevent fires?
Well, the basics. Keeping work areas really clean, monitoring equipment, and critically replacing damaged cords or wires immediately.
And there's that specific scenario with broken wires inside a cord.
Yes, that's where it gets really interesting and dangerous. If only a few wires break inside a power cord, all the current has to travel through the remaining unbroken wires.
Right, the path narrows.
Exactly. That significantly increases the current density in those few wires. It generates excessive, sometimes catastrophic heat, melts the insulation, and boom, that's a fire waiting to happen.
Okay, that raises a critical question then. How do we manage other high-pressure systems safely? Let's talk about compressed gas safety.
Right, and here we have some absolute never rules. Just Never do these things.
Like what?
Never, under any circumstances, use compressed air to clean your hands or clothing.
Why not? Seems quick.
Because the pressure can actually force debris, fine dust particles, whatever's on your skin, deep into the flesh. That can potentially lead to a really nasty, even fatal infection.
Wow, okay. Never knew that.
And similarly, never spray compressed air near other personnel. Same reason, plus the risk of eye injury.
Okay, noted. Now, there's a specific important distinction you mentioned regarding high pressure in tires.
Yes, you absolutely must use tire cage guards when you're inflating a wheel assembly that is off the aircraft.
Off the aircraft, got it.
But once that tire and wheel assembly is bolted onto the aircraft landing gear, those cages are not required when you're merely adjusting the pressure.
Okay, what the difference there? Seems inconsistent at first glance.
Well, think about the physics involved. When the wheel is off the aircraft, there's nothing substantial to contain the immense force of a potential blowout. That rim could become shrapnel. The cage provides that essential containment. But once the wheel is installed, bolted securely to the landing gear structure, the airframe itself provides sufficient containment against a catastrophic failure.
So the cage becomes redundant just for topping up the pressure.
Exactly. That's the key safety differentiator you need to understand.
Good clarification. That makes sense. Okay, let's jump to what feels like the universal language of immediate hazards, hazardous materials, or AGI-BAT.
Right, and you absolutely must know the materials safety diamond, sometimes called the risk diamond.
The four colored squares.
Precisely. It's segmented into 4 colors. Red for flammability, yellow for reactivity, blue for health hazards.
And the white one.
The white segment is reserved for special hazards, things like oxidizers, water-reactive materials, that sort of thing. And the numbers inside, 0 to 4.
0 is basically no hazard, 4 is extremely hazardous.
You got it. 0 means little or no hazard, 4 means very hazardous. It gives you that immediate risk level assessment.
But for the really detailed breakdown, the chemical formulas, emergency actions, long-term risks.
For that, you must consult the detailed safety data sheets, the SDSs. And remember, OSHA legally requires these to be readily available wherever these materials are used or stored. You need to know where to find them.
Okay, shifting gears a bit to the heavy environment. Let's briefly cover machine tool safety. You know, lathes, drill presses, grinders.
Sure, some universal precautions here. Always wear eye protection, obviously. Yep. Always securely clamp your work. Don't try to hand-hold something on a drill press, for example.
Right.
And specifically for grinders, never try to force the grinding wheel onto the spindle. Let it slide on easily.
And there was a point about where to stand.
Yes. This is a critical, potentially life-saving practice. Do not stand directly in the plane of rotation, the arc of the grinding wheel, during operation.
Why is that?
Just in case the wheel shatters or explodes due to the high rotational force or an internal flaw, you don't want to be in the line of fire.
Makes sense. Okay, that sets the stage perfectly for one of the highest risk maintenance ops.
Yeah.
Welding safety.
Definitely high risk. Welding really must be performed in designated, properly equipped, isolated areas. Or better yet, remove the part from the aircraft entirely and weld it elsewhere.
But sometimes you have to weld on the aircraft, maybe in the hangar.
It happens. But if you absolutely must weld on an aircraft inside a hangar, the precautions multiply significantly.
Like what?
Okay, you cannot have open fuel tanks anywhere nearby. You can't be working on fuel systems. No painting is permitted in the vicinity. And critically, no other aircraft are allowed within 35 feet of the welding operation.
35 feet, that's a big zone.
It is. And beyond just the separation distance, you need qualified welders, obviously. You need a dedicated fire watch constantly monitoring the area with no other duties.
Right.
And specific fire extinguishing equipment must be ready. A minimum 20B rated extinguisher nearby with a much larger 80B rated backup readily accessible.
Wow. Okay. And there was something about the aircraft itself.
Crucially, yes. The aircraft being welded on must be in a towable condition. That means the parking brakes have to be released, and a tow tug must be attached and ready to move the aircraft immediately if a fire breaks out.
That's a huge list of precautions just for welding. If I had to guess, which one gets forgotten most often? Is it maintaining that 35-foot separation, or maybe remembering to release the brakes and hook up the tug, which is the compliance trap?
That's a good question. I'd say it's probably the combination of the tug attachment and the brake release.
Why that?
Well, think back to human factors. Attaching the tug. It's an extra step. It feels a bit tedious, maybe. If a technician is feeling complacent or under deadline pressure,
You might skip it.
they might. But failing that one step means that entire multi-million-dollar asset cannot be moved quickly if a fire erupts. That one piece of compliance, ensuring it's towable, is absolutely paramount.
Excellent point. Linking that procedure right back to the cognitive stress we talked about earlier.
Yeah.
Okay, let's step outside now and face flight line safety.
Right. And the number one critical hazard out there is FOD, foreign object damage.
Little things causing big problems.
Exactly. And if we connect this to the physics of turbine engines, they create this massive low-pressure area in front, basically acting like a giant vacuum cleaner.
Sucking things in.
Sucking in tools, hardware, debris, anything loose. And the exhaust end. It can propel small objects great distances at potentially lethal speeds.
So controlling FOD is key. How do we do it?
Control methods have to be strict. Keeping the ramp and operational areas scrupulously clean is number one. Maintaining a highly rigorous tool control program, know where every tool is.
Right. Accountability.
And ensuring convenient receptacles are available for everything. Safety wire scraps, broken zip ties, loose rivets. Everything needs a place to go that isn't the ramp.
And we can't forget the noise out there. It's loud.
Extremely loud. You absolutely must use hearing protection, either external muffs or internal earplugs.
For what kind of noise?
For the constant high noise levels generated by running aircraft engines, auxiliary power units, APUs, fuel trucks, even loud hand tools like rivet guns or pneumatic drills used on the line.
And it's not just about comfort, is it?
Not at all. Even short-duration exposure to those high-frequency sounds causes cumulative, permanent hearing damage over time. Protect your hearing from day one.
Okay. Now, a specific type of aircraft, helicopter safety. You mentioned there are different risks.
Completely different risks you need to learn. The cardinal rule, the absolute number one thing, never, ever approach a single rotor helicopter from the rear while its blades are turning.
Why the rear specifically?
Because the tail rotor is often practically invisible when it's spinning at speed. It's a deadly hazard you might not even see.
So how should you approach?
You must always approach in the pilot's field of vision, typically from the front or side, and make eye contact if possible. If you need to get to the other side, go around the nose, never the tail.
Got it. Around the nose. Okay, let's talk about moving aircraft on the ground. Towing procedures.
Right. First rule, a qualified person must be in the flight deck, in the cockpit,
Why?
to operate the aircraft brakes. In case the tow bar fails or there's unexpected movement, someone needs to be able to stop the aircraft immediately.
Makes sense. And the speed.
Towing vehicle speed must be reasonable. Basically, don't go faster than the walking speed of the team members around the aircraft. Keep it slow and controlled.
And there's that critical check related to the nose wheel steering. You mentioned it ties back to human factors.
Yes, this is a big one. For aircraft equipped with a steerable nose wheel, the steering lock scissors mechanism must be set to the full swivel position before you start the tow.
Full swivel before towing.
Correct. And just as importantly, it must be reset to the locked position for steering after the tow bar is removed.
And if you forget to set it to swivel before turning.
You risk damaging or even destroying the nose wheel steering mechanism with the very first turn of the tow vehicle. It's an expensive, easily avoidable mistake.
Okay, crucial check. Now let's cover engine starting essentials.
All right. Before starting any engine, ideally the aircraft should be positioned facing into the prevailing wind. Helps with cooling.
Good tip.
And you must ensure the safe, clean removal of any external power cables before the engine lights up. Don't want those getting sucked in or tangled.
And the fire guard.
Absolutely essential. A dedicated fire guard. Someone who is completely familiar with the specific starting procedures for that aircraft and engine.
Yeah.
Equipped with a suitable CO2 extinguisher, minimum 5-pound capacity, must be stationed in an appropriate place where they are clearly visible to the pilot or person starting the engine.
Got it. Now, there's some specifics for reciprocating engines, particularly radials.
Yes, the big round engines. We have to deal with the risk of hydraulic lock.
What's that?
It's when oil leaks past the piston rings into the lower cylinders while the engine is shut down. If enough oil collects, it can stop the piston from completing its stroke because liquid doesn't compress.
Ah, okay. So how do you check for it?
Before starting any radial engine that's been shut down for more than about 30 minutes, you must check for this condition. You do it by carefully turning the propeller by hand through 3 or 4 complete revolutions in the normal direction of rotation.
And what if it stops abruptly?
If it stops hard, that's likely a hydraulic lock. The absolute rule here is Never use force to try and turn the prop through the lock. You'll bend or break a connecting rod.
Okay, so what do you do?
You have to remove a spark plug from the lock cylinder, drain the oil, and then proceed. And never turn the propeller backward to try and clear a lock.
Got it. And what about hand propping these engines if necessary?
If hand propping is required, always assume the ignition switch is on and in, even if you think you just turned it off. Treat it as live.
Safety first.
Absolutely. And push the blade down sharply using the palms of your hands. Do not grip the blade with your fingers wrapped around it.
Why not?
Because if the engine kicks back, which they can do violently, it will likely break your fingers or wrist. Palms allow your hands to slip on safely.
Okay, good technique. Now, shifting to turbines. Turbine engine start failures. You need to be able to define and differentiate them quickly, right?
Immediately. A hot start is probably the most dangerous. That's when the EGT, the exhaust gas temperature, exceeds the specified limits during the start sequence.
And what usually causes that?
It's usually caused by an excessively rich fuel-air mixture lighting off. Too much fuel too soon.
So what's the action?
If you see that EGT spiking, heading towards the limit or exceeding it, shut off the fuel immediately. That's the critical action.
Okay, and the other type, a false or hung start.
Right. A false or hung start is different.
Yeah.
The engine successfully lights off, you get combustion, but the RPM fails to accelerate normally. It just hangs, stabilizing at some abnormally low RPM instead of spooling up to idle.
So it starts, but doesn't reach self-sustaining speed. What do you do then?
Same immediate action, essentially. Shut down immediately by cutting the fuel.
Okay. And is there a procedure after any unsatisfactory start?
Yes. Regardless of whether it was a hot start or a hung start, if any unsatisfactory start occurs, you turn off both the fuel and the ignition. But then you continue rotating or motoring the compressor for approximately 15 seconds.
Why motor it after shutting off fuel?
That procedure is absolutely essential for scavenging any accumulated raw fuel from the hot section of the engine. It clears it out before you attempt another start, preventing a potentially worse hot start or fire on the next try.
Makes sense. Purge the system. Okay, now for the foundation of safety response itself, fire protection.
Right. And we start with the basics, the fire triangle. The three elements required for any fire are fuel, heat, and oxygen.
And the principle is?
Remove any one of those three elements, break the triangle, and the fire goes out. That's the basis for all firefighting.
And we classify fires, don't we?
We do, because different fuels require different extinguishing agents. Class A is your ordinary combustibles, wood, paper, cloth. Class B involves flammable liquids and greases, fuel, oil, hydraulic fluid.
C is electrical.
Class C is energized electrical equipment. The key is energized. If you cut the power, it might become a Class A or B fire. And Class D?
Metals.
Class D is flammable metals like magnesium, titanium, sodium, things you might find on aircraft structures or components.
Okay, so knowing the class tells you what fire extinguisher to use, or maybe not to use.
Exactly. Water, for instance, is great for Class A. But it's dangerous for Class B. It can spread the burning liquid. It's dangerous for Class C if the power is still on because water conducts electricity.
And Class D.
Absolutely catastrophic for Class D metal fires. The water hitting molten metal can cause it to basically explode due to rapid steam expansion. Very dangerous.
Okay, so water is limited. What about CO2?
Carbon dioxide, CO2, is fine for Class A, B, and C fires. It works by displacing oxygen and cooling, but it's not effective on Class D metals. And a big caution, CO2 displaces oxygen, so in a confined space, it can actually asphyxiate the operator. You need to be aware of that.
Right. So for aircraft, especially Class B and C fires involving fuel or electrics, what's preferred?
For aircraft, we generally rely on halon extinguishers, specifically halogenated hydrocarbon extinguishers like halon 1211, which is a liquid streaming agent, and halon 1301, which is a gaseous flooding agent often used in fixed systems.
And why are they preferred?
They are highly effective on B and C fires. They are colorless, they're non-corrosive, they leave no residue, which is great for sensitive avionics, and most importantly, they interfere chemically with the combustion chain reaction, stopping the fire very quickly.
But there's a huge toxicity warning somewhere in here, right?
Yes, this is absolutely critical, something you must carry forward throughout your entire career. Carbon tetrachloride, sometimes historically referred to as halon 104,
Okay.
is extremely toxic. It carries a UL toxicity rating of 3, which is very high.
Okay.
It produces lethal phosgene gas when it hits heat. It is absolutely not approved for any fire extinguishing use today.
So if you find an old extinguisher with carbon tet.
Treat it as hazardous waste. It needs to be disposed of according to very strict environmental regulations. Do not discharge it. Do not keep it around. It's dangerous.
Understood. Okay, what about dry powder extinguishers?
Dry powder agents are excellent for Class D metal fires. They smother the burning metal. However, they're generally not recommended for general aircraft use because the powder residue is incredibly corrosive and very difficult to clean up, especially from electronics or engine components.
Right, causes more problems later. Okay, briefly touching on securing aircraft. Tie-downs.
Yeah, important for preventing ground movement in wind. For light aircraft, you need to use proper anti-slip knots, like the bow line. It's strong, but can be untied easily even after being loaded.
And for heavy aircraft.
For heavy aircraft, besides tie-downs, you need to install control surface locks to prevent wind damage to flight controls, and always use wheel chocks. And a key point. Tie-down ropes should never be attached to wing lift struts. Attach them to the designated tie-down rings on the aircraft structure.
Good tip. Okay, final major section. Fuel servicing hazards.
Huge area of risk. Remember, it's the fuel volatility, its ability to evaporate easily, that creates the primary hazard. It's the fuel vapor, not the liquid itself, that burns.
And static electricity.
Static electricity is a massive concern, especially with fuel. Aircraft build up a huge static charge just flying through the air, or even from fuel flowing through hoses.
So you need a specific procedure.
A critical 3-step safety protocol you must always follow. First, the aircraft must be grounded to dissipate its static charge to the earth. Second, the aircraft must then be bonded to the fuel truck or the fuel pit system to equalize the electrical potential between them.
Ground first, then bond.
Yes, and only after both grounding and bonding are properly completed do you open the aircraft fuel tank cap. This prevents any static spark from igniting those fuel vapors when the tank is open.
Crucial sequence. And fuel contamination.
Always a concern. The final piece is ensuring the correct fuel type and grade is used. AVGAS, aviation gasoline, is color-coded for different grades. Jet fuel is usually clear or straw-colored, but the refueling equipment, pipes, and placards should be clearly marked, usually with black lettering. Putting the wrong fuel in an engine can be catastrophic.
And speaking of contamination control, what about servicing oxygen systems?
Yes, another critical area. You must use aviators breathing oxygen, ABO. It has to be ABO.
Not industrial oxygen, or even medical oxygen.
Never use industrial or medical oxygen. Why? Medical oxygen, while pure, is allowed to contain a small amount of water vapor.
And water at altitude.
That water will freeze at the high altitudes where aircraft operate. It can form ice crystals that block oxygen lines or regulators, leading to hypoxia. ABO has almost zero moisture content.
Okay, good distinction.
And one more huge oxygen hazard. Oxygen, even ABO, forms highly explosive mixtures when it comes into contact with even trace amounts of oil or grease. Oxygen servicing equipment must be kept scrupulously clean and never handled with greasy hands or tools.
Wow, okay, so recapping here. What does this all really mean for you, the student? We've covered a huge range from managing your own stress that can cause errors, to the critical steps of bonding before fueling, to the dangers of invisible tail rotors.
Yep.
This deep dive should really give you a foundational appreciation for why all these rules and procedures exist. They weren't just made up. They're often written in blood, or based on preventing catastrophic failures that have happened before.
That's exactly right. And if we try to connect this to the bigger picture again, remember that safety is layered. We talked about how human factors connects directly to procedures like remembering to release the parking brake before welding, or always setting the steering lock to full swivel before towing. Every rule, every check, it often serves multiple safety purposes simultaneously. Understanding the why makes you much more likely to follow the how.
So you learned today that a hot start requires immediately shutting off the fuel. You learned that static electricity during fueling demands that meticulous grounding and bonding sequence. Considering the sheer range of these instantaneous, potentially lethal hazards we covered, from that invisible tail rotor to the extreme toxicity of old Halon 104 to a grinding wheel exploding, which single procedural step, maybe something seemingly small like always using a tire cage when required or always checking for a hydraulic lock on a radial engine, which one do you think statistically saves the most lives over the course of an entire AMT's career?
Hmm, that's a tough one to quantify.
It is something to think about. Keep asking the why behind every single procedure as you move through your course, because that deep understanding, not just memorization, is what truly keeps the skies safe for everyone.